Hey there, here we go into L'Hopital's rule. So basically, we've now learned a bunch about e to the x and ln x. So we're actually going to dive way back when into limits. And the reason why we're going way back into limits is there's this skill called L'Hopital's rule that's going to allow us to evaluate limits where when we use direct substitution, we get 0 over 0 or infinity over infinity. I'm fitting that in with e to the x and ln x because some of those limits involve these values, and we're going to be using the derivative. Now that we've learned the derivatives of both of those, we can rock L'Hopital's rule with any function. So essentially, here's what we got. Anytime you plug in some limit, so as x approaches a of some function, you plug in a and you get 0 over 0 or infinity over infinity, then the limit as x goes to a of one function over another function will be equal to the very same limit as x approaches a of the derivative of the numerator over the derivative of the denominator. Let's see this one in action. So always start out with direct substitution. So I'm going to plug 3 into this thing, and I get 3 squared minus 9 all over 3 minus 3. And that gives us 9 minus 9, right? So 9 minus 9 over 3 minus 3, nothing extreme yet. Ooh! That's 0 over 0. Now, while you learned that you could factor the numerator and cancel out common factors to evaluate it, there's another way of doing this. So what we can actually now do, now that we're in indeterminate form, is we take the limit as x approaches 3 of the derivative of the numerator, which is just 2x, all over the derivative of the denominator, which is just 1. Notice we're not using the quotient rule here. You're just straight up taking the derivative of the numerator, derivative of the denominator, and now just evaluate the 3 in and see what we get. So that'll be 2 times 3, straight up substitution, all over 1, which is 6. And that is your limit. So why does this work? Well, without going into a heavy proof, the idea is this. Basically, we're saying that the limit as x approaches 3, because it goes to 0 over 0, the limit of the rates of those two functions approaches the very same limit. So we're basically comparing the rate of how fast this is going to that rate, and that is going to give you the same limit as if we used another method. That's pretty cool. That's pretty darn nifty, I think. So the old school way, just to kind of throw that out there to show you that it is indeed 6, we would factor out x squared minus 9. So you get x minus 3 times x plus 3 all over x minus 3, and these divide out. And then we plug in 3, and 3 plus 3 is 6. So old school was 6, new school was 6. Doesn't matter which method you use for this, but here's the key. Anytime you get 0 over 0 or infinity over infinity, what we then know is, we can use L'Hopital's rule. And let's do a little more practice on that. All right, so we'll do a few more problems with that practice, and then we'll call it a video before getting into some other forms with L'Hopital. So this says, find the following limits. Be careful to only apply L'Hopital where direct substitution leads to an indeterminate form. Remember, that's 0 over 0 or infinity over infinity. Okay, so looking at this, always start out with direct sub. That's going to be e to the 2 times 0 squared is 0, minus 1 all over 0 squared, which is 0. That's equal to 1 minus 1 over 0, which is 0 over 0. So it's indeterminate. Therefore, we can use L'Hopital's rule. So I've got the limit as x goes to 0 of. Now the derivative of e to the stuff, well, is e to the stuff d stuff. So that'd be times 4x. We know that from previous videos. Derivative minus 1 is 0. All over the derivative denominator is 2x. Ooh. Now what we're going to notice here is those x's divide out. So does the 4 and the 2. So we're left with the limit as x goes to 0 of 4e to the 2x squared all over 2. Now, we reevaluate once we've done the L'Hopital step. So we plug in 0, you get e to the 0 squared is 0 times 2 is 0. So we get 4e to the 0 all over 2. That's equal to, well, e to the 0 is 1 times 4 is 4 divided by 2 is 2. So that's your limit. We know that we're done applying L'Hopital because we did not get 0 over 0 when using direct substitution. You don't want to fly by and just keep taking derivatives in numerator and denominator. You stop doing that the second you get a non-indeterminate, so a determinate form. I was going to say non-indeterminate, it's a double negative. Okay, on to this one. Now there's two ways of evaluating this. In old school, you looked at this, the limit as x goes to infinity. Well, that's just going to be the ratio of the leading coefficients, right? That's 1 over 3. So you could look at this and say the ratio of the leading coefficients, since the degrees are the same, is 1/3. Okay? Or when we do direct substitution, you'll note that we're going to get infinity over infinity. So that's one way, or this way. So we're going to use L'Hopital just to kind of show you that it works. So the derivative of the numerator is 2x minus 5. All over, this would be 6x plus 1. And we reevaluate the infinity in there, but that's still going to leave you with infinity in the numerator over infinity in the denominator. The 1 and the 5 don't matter. Those x's do. So we use L'Hopital again. And this problem is actually a microcosm for why L'Hopital works. Take the limit as x goes to infinity. The derivative of the numerator is 2. Of the denominator is 6. And hey, that simplifies to 1/3. Nice. Good job. Fist bumps. Okay, so looking at something like this, you've got 1/3. We already knew that from before, but this is why L'Hopital works. As we go to infinity over infinity, the limit becomes all about the race between the numerator function and the denominator function. So we want to know, what are the rates at which they approach infinity? And those rates, the ratio of those rates, that gives you the limit. Wait a second. The ratio of the rates. The ratio of the derivatives. L'Hopital. It's very cool. Okay, we got 2 more in this video, and let's check them out. It says find the following limits. Be careful to only apply L'Hopital, where direct substitution leads to an indeterminate form. Okay, so direct sub in, we'll plug in 0. 0 to the 5th is 0 times 11, 0. Minus 14.5. Ah. All over, 0 cubed is 0 plus 0 is 0. That's negative 14.5 over 0. Now be very careful here. So this is undefined. So I'll just put DNE. The limit does not exist. You cannot use L'Hopital. It is not indeterminate form. It is quite determined, actually. The upper function has a much higher power than the lower function. And with that, we still end up with 0 in the denominator, though. We're not going to infinity. So we can't use any other rules. That's it. It's not determined. Get a number over 0. And that's pretty darn large. That's because, if you forget, you've got a number over a very small number is a massive number. So the limit does not exist. How about this one? Let's plug in infinity. And so we'll get ln of infinitar on over infinity squared. Ln of infinity goes to infinity over infinity. So that's indeterminate form. So we will apply L'Hopital's rule. So that's going to be the limit as x goes to infinity of, well, the derivative of the numerator is 1 over x. The derivative of the denominator is 2x. When you simplify this, this is 1x times 1 over 2x. That's really what's going on when you divide by 2x, which is equal to 1 over 2x squared. So that's the limit that we're now going to evaluate. So L'Hopital's been applied once. We don't keep applying it. We want to see what we're left with here when we evaluate in infinity. So as we evaluate in infinity, 1 over, essentially we get 1 over infinity, because 2 times infinity squared is large. And 1, a small number, over a gigantic number is 0. And that's your limit. So I'm going to point out, if you're doing this on an A, B, or BC exam, you're going to want to say indeterminate form. And then I might state using L'Hopital. The reason why is you want to communicate what it is that you're doing here to all of a sudden magically take derivatives of the numerator and denominator. And again, state that you're in indeterminate form to say, hey, I know I can use L'Hopital because I'm in indeterminate form. All right, in the next video, what you and I are going to be rocking are more L'Hopital problems, but of different types of indeterminate forms. That's right, there's more than just 0 over 0 and infinity over infinity. I am stoked to see you there, but until then, peace.